Welcome! In this session, we'll be tackling problem number 466, count the repetitions. This problem involves analyzing string repetitions and optimizing the process to achieve the desired result efficiently. Let's explore the challenge, break it down, and solve it step by step. In this problem, you are tasked with determining how many times a specific string can be formed as a subsequence within another string that is repeated multiple times. You're given two strings, s1 and s2, and two integers, n1 and n2. The goal is to calculate the maximum integer k such that s2, repeated k times, can be formed as a subsequence of s1, which itself is repeated n1 times. A subsequence is defined as a sequence that can be derived from another string by deleting some or no characters without changing the order of the remaining characters. For example, ABC is a subsequence of EBC. The input format includes the strings s1 and s2, as well as the integers n1 and n2, with the constraints that the lengths of s1 and s2 range from 1 to 100 and n1 and n2 can go up to 1 million. The output is an integer representing the maximum number of times s2, repeated n2 times, can fit as a subsequence within s1, repeated n1 times. To clarify the problem further, consider this example. Suppose s1 is ACB, n1 is 4, s2 is AB, and n2 is 2. When s1 is repeated n1 times, we get the string ek back. Similarly, when s2 is repeated n2 times, we get ABAB. The task is to determine how many times ABAB can be formed as a subsequence within ek back. By analyzing the sequences, we can see that ABAB can be constructed twice as a subsequence. Therefore, the output for this example is 2. Another example illustrates the problem further. Here, S1 is Baba, N1 is 11, S2 is Bob, and N2 is 1. When we repeat S1 11 times, we get the string Baba. When we repeat S2 just once, we get Bob. Now, we check how many times Bob can be formed as a subsequence within the repeated Baba string. Through careful analysis, we find that the subsequence Bob can be extracted 7 times. Thus, the output for this example is 7. Here's one more example to reinforce the concept. If S1 is AAA, N1 is 3, S2 is AA, and N2 is 1, repeating S1 3 times gives us the string AAA, and repeating S2 just once gives us AA. By examining the repeated AAA string, we can determine that AA can be formed as a subsequence 4 times. Hence, the result for this case is 4. These examples highlight how the problem involves identifying subsequences within repeated strings and calculating the maximum possible repetitions. The problem comes with several constraints and edge cases to consider. For example, the length of both S1 and S2 is between 1 and 100, while N1 and N2 can be as large as 1 million. Both strings consist only of lowercase English letters. Additionally, the output k will always be an integer. Some edge cases include scenarios where S1 and S2 have no common characters, meaning no subsequences can be formed, resulting in an output of 0. Another edge case occurs when S2 is longer than S1 but can still be formed as a subsequence when S1 is repeated multiple times. Finally, if S1 and S2 are identical, the problem reduces to counting how many times S2 can fit within the repeated version of S1. These considerations ensure the solution is both comprehensive and robust. To start, let's consider the brute force approach to solving this problem. The idea here is straightforward. We simulate repeating the string S1 exactly n1 times, and then we check how many subsequences of the repeated string S2, repeated n2 times, can fit into it. The way this works is by iterating over every character in S1. For each character, we compare it to the current character in S2. If there's a match, we move to the next character in S2. Once we complete one full repetition of S2, we increment our count and continue until we've exhausted all repetitions of S1. While intuitive, this method has a significant limitation: its inefficiency. The time complexity here is O, N1 multiplied by the length of S1 multiplied by N2 and the length of S2, which grows prohibitively large given the constraints. With N1 and N2 both going up to 10 to the power of 4, this approach quickly becomes infeasible for larger inputs. Now, let's discuss the optimized approach and the key insight that makes it work. The breakthrough here lies in recognizing that, as we repeat S1 and try to match S2 as a subsequence, a periodic pattern eventually emerges. This periodicity allows us to avoid redundant computations and optimize the process significantly. To achieve this, the first step is to track matches across repetitions. Instead of simulating all N1 repetitions of S1, we keep track of how many repetitions of S2 can be matched after each repetition of S1. The second step is to detect cycles. As we simulate the matching process, we use a hash map to store the current state. This includes the position in S2 and the count of S2 repetitions completed at the start of every repetition of S1. If we encounter the same state again, it means a cycle has been detected. Finally, once we've identified a cycle, we can skip redundant computations by calculating the contribution of the cycle in terms of matches for S2, and then jump ahead, skipping unnecessary repetitions of S1. This drastically reduces the number of iterations required. By leveraging periodicity, the optimized approach reduces the time complexity to O, N1 multiplied by the length of S1, which is far more manageable and efficient. The chosen strategy for this problem is the optimized approach, as it is both practical and efficient. By taking advantage of periodicity, it minimizes unnecessary computations and ensures the solution scales well for large inputs. When comparing the two methods, the brute force approach is simpler to implement but completely impractical for large inputs due to its high time complexity. On the other hand, the optimized approach, while slightly more complex to implement, handles large inputs effectively without compromising correctness. Given the constraints of the problem, the optimized approach is clearly the better choice as it provides a significant reduction in computational overhead while ensuring accuracy. By focusing on detecting and leveraging cycles, we achieve a solution that is both elegant and efficient, making it ideal for this problem. In this problem, we are tasked with finding out how many times a string S2, repeated N2 times, can be formed as a subsequence from another string S1, repeated N1 times. A key challenge here is the computational cost of simulating the full repetition of these strings, especially when N1 or N2 is very large. Instead, we focus on the relationship between their characters and how subsequences align. For example, if S1 is ABC and S2 is AB, the subsequences of S2 depend on the positions of A and B in S1. To solve this, we break the problem into smaller steps. First, we track how many times S2 fits into S1 as a subsequence during each cycle of S1. Then, we use this information to extrapolate for the given values of N1 and N2. By doing this, we avoid the inefficiency of directly simulating the full repetition of strings. To achieve this, we use a two-pointer technique to track how characters in S1 and S2 match. One pointer, I, is used for S1, and the other, J, is used for S2. When S1, I, matches S2, J, both pointers are advanced, indicating that we've matched the current character of S2. If there's no match, only I is moved forward. When the pointer J reaches the end of S2, it resets to 0, and we increment a count to track how many times S2 has been completed. This process is repeated for one full cycle of S1, allowing us to record how many full repetitions of S2 are achieved in that cycle. As we simulate S1 for N1 cycles, we also monitor the positions of the pointers and the completed counts. If patterns or cycles are detected, such as repeating pointer states, we can use this information to optimize the computation by extrapolating results for the remaining cycles, rather than simulating them all. The key insight here is to avoid fully simulating the repeated concatenation of S1 and S2, as it would be computationally expensive for large values of N1 and N2. Instead, we rely on detecting patterns in how characters align across cycles. Over time, the alignment of S1 and S2 will form a repeating cycle. Once this cycle is detected, we can leverage it to calculate the result more efficiently. The two-pointer technique ensures that characters are processed without unnecessary comparisons, while a hash map or similar data structure is used to track the state of pointers and completed repetitions. This allows us to identify cycles and determine their properties, such as how many S2 repetitions they complete. By extrapolating from these cycles, we compute the result for large inputs without explicitly processing all repetitions of S1. Using this approach ensures efficiency while maintaining accuracy. When solving this problem, it's important to consider edge cases. For instance, if no character in S1 matches any character in S2, the result should be 0. On the other hand, if S1 and S2 are identical, the result is simply the floor of N1 divided by N2. Additionally, when the lengths of S1 and S2 differ significantly, we must ensure that the pointers stay within bounds and process the strings correctly. For small values of N1 or N2, we need to ensure that the algorithm doesn't rely solely on cycle detection, as there might not be enough data to form a cycle. From a complexity standpoint, the algorithm runs in O, N1 len, S1, for simulating and detecting patterns, and subsequent computations are constant time. The space complexity is O, len, S2, as we only need to store pointer states and counters. This makes the approach both scalable and efficient. Let's walk through an example. Suppose S1 is ABC, repeated 4 times, and S2 is AB, repeated 2 times. First, we simulate one cycle of S1. As we iterate through S1, we match the characters at NB from S2, completing one full repetition of S2. Repeating this process for subsequent cycles, we observe that after 2 cycles of S1, a pattern emerges. Using this pattern, we can extrapolate the results for the remaining cycles without further simulation. In this case, we calculate the total number of completed repetitions of S2 and divide it by N2 to determine the maximum number of complete subsequences. The final result is 2, as S2 can be fully formed twice within the given repetitions of S1. This Python implementation solves the problem by analyzing the pattern formed when traversing S1 repeatedly to create subsequences of S2. The goal is to efficiently count how many times S2 can be formed as a subsequence when S1 is repeated N1 times. 1. Initialization. We start by determining the lengths of S1 and S2. We initialize count 1 to track the number of S1 repetitions processed, and count 2 to track the number of S2 characters matched. We also create a dictionary index 2_map to detect cycles during processing. 2. Outer loop. The while loop runs until we've processed all repetitions of S1, up to N1. For each character in S1, we check if it matches the current character in S2, tracked by count 2% len2. Every match increments count 2. 3. Cycle detection. After processing a full S1, we check if the current count 2% len2 has been seen before an index 2_map. If it has, a cycle is detected. We calculate the cycle length, cycle_length, and the number of S2 matches in one cycle, cycle_count2. Using this information, we skip processing the remaining cycles by directly adjusting count 1 and count 2. For update map, if no cycle is detected, we store the current state of count 1 and count 2 in index 2_map for future cycle detection. 5. Result calculation. After all repetitions of S1 are processed, the result is given by count 2 // N2 len2, which calculates the total number of full S2 repetitions achieved. This approach avoids unnecessary computation by leveraging cycle detection and efficient skipping, ensuring the solution is optimal for large input sizes. Here, we begin with the Java implementation of the solution. The function getMaxRepetitions takes in 4 parameters, S1, N1, S2, and N2. The goal is to determine how many times S2 can be repeated within the repetitions of S1. First, we initialize the lengths of the 2 strings, len1 and len2, and set up counters count 1 and count 2 to track the number of repetitions of S1 and the number of characters in S2 matched so far. We also create a map, index2map, to detect and handle cycles during the iteration. Next, we begin a while loop that continues until count 1 reaches N1, which represents the total repetitions of S1. Inside the loop, we iterate over each character of S1. If a character matches the current character of S2 based on the count 2% len2 index, we increment count 2 to track the match progress in S2. After processing all characters of S1, we increment count 1, as one full repetition of S1 is complete. Then, we calculate the modulo index of count 2 with respect to len2. This index helps us identify patterns or cycles. If the map already contains this modulo index, it means a cycle is detected. We retrieve the previous state stored in the map, calculate the cycle length in terms of S1 repetitions, and the progress made in S2 during that cycle. Using this information, we calculate how many complete cycles can fit into the remaining repetitions of S1 and adjust count 1 and count 2 accordingly, effectively skipping redundant iterations. If no cycle is detected for the current modulo index, we store the current state of count 1 and count 2 in the map for future reference. This ensures that if the same state is encountered later, we can identify the cycle and optimize the computation. Finally, after processing all repetitions of S1, we calculate the result by dividing count2 by the total number of characters in S2 across n2 repetitions, which is given by n2 * len2. This division gives us the maximum number of times S2 can be fully repeated within the given constraints. The function then returns this value as the result. To solve this problem, we begin by examining example 1 where S1 is ABC, repeated 4 times, and S2 is AB, repeated 2 times. First, we initialize variables. len1 and len2 store the lengths of S1 and S2, respectively, while count1 and count2 keep track of how many times we've processed S1 and matched characters in S2. We also maintain a mapping, index2_map, to detect cycles by recording the state of count1 and count2 when a complete match of S2 is found. In the first iteration of the outer loop, we traverse S1 character by character. The first 2 characters, A and B, match sequentially with S2, so we increment count2 twice. The third character, C, does not match, so we only increment count1 after finishing the traversal. Since count2% len2 equals 0, this indicates that we've completed one full repetition of S2, and we record count1, count2 in index2_map. In the second iteration, we traverse S1 again, and another full repetition of S2 is matched, bringing count2 to 4. At this point, we detect a cycle in index2_map because the state, count1, count2, repeats. By analyzing the cycle, we determine that its length is one outer loop iteration, and the cycle contributes 2 full repetitions of S2. Using this information, we skip ahead to complete the remaining iterations efficiently, updating count1 to 4 and count2 to 8. Finally, we calculate the result as the number of full repetitions of S2 that fit into count2, which is 8 divided by 2 times 2, giving us 2. The output for example 1 is 2. Now, let's move to example 2 where S1 is ACB, repeated 4 times, and S2 is still AB, repeated 2 times. Again, we initialize the same variables. During the first iteration, we traverse S1 and observe that the first character, A, matches the first character of S2, so we increment count2. The second character, C, does not match, but the third character, B, matches the next character of S2, completing one full repetition of S2. This brings count2 to 2, and we increment count1 after finishing the traversal. Since count2% len2 equals 0, we record count1, count2 in index2_map. In the second iteration, we traverse S1 again and match another full repetition of S2, bringing count2 to 4. At this point, we identify a cycle because the state, count1, count2, repeats. By analyzing the cycle, we determine its length is one iteration, and it contributes 2 full repetitions of S2. This allows us to efficiently skip ahead to complete the remaining iterations. Using the cycle information, we compute the remaining iterations. The cycle length is 1, and since 2 iterations remain, we skip directly to count1 equaling 4 and count2 equaling 8. At the end, we calculate the result as the total number of complete repetitions of S2 that fit into count2. This is count2 divided by n2 times len2, which equates to 8 divided by 2 times 2, giving us a result of 2. The output for example 2 is also 2. Now, consider example 3, where S1 is A, repeated 100,000 times, and S2 is AAA, repeated once. The initialization is similar, but since S1 contains only one character, the traversal process is straightforward. In the first iteration, the single character in S1 matches the first character of S2, so we increment count2 to 1. After finishing the traversal, we increment count1 to 1 and record count1, count2 in index2_map because count2% len2 equals 1. As we continue processing S1, we detect a repeating cycle every time count2% len2 repeats. The cycle length is determined to be 5 iterations, and each cycle contributes 5 matches to count2. Using this information, we skip ahead to complete all remaining iterations efficiently, setting count1 to 100,000 and count2 to 500,000. Finally, we calculate the result as the total number of complete repetitions of S2 that fit into count2. This is count2 divided by n2 times len2, which equates to 500,000 divided by 1 times 5, giving us a result of 100,000. The output for example 3 is 100,000. To analyze the time complexity of the algorithm, let's break it down step by step. The outer while loop is the first component to consider. This loop continues running until the value of count 1 reaches n1. Therefore, in the absolute worst case where no cycles are detected, the loop will execute exactly n1 iterations. However, the algorithm includes a cycle detection mechanism, which can terminate the loop earlier if a repeating pattern is found, making the actual number of iterations potentially smaller in practice. Inside this outer loop, we have an inner for loop that iterates over each character of S1. If we denote the length of S1 as len1, this means the inner loop will run len1 times for every single iteration of the outer loop. Combining both loops in the worst case results in O, n1 asterisk len1, total iterations. Additionally, the cycle detection process uses a dictionary called index2_map to store previously encountered states. Each operation, whether checking or inserting a key value pair into the dictionary, takes constant time, or O1. Since the dictionary only needs to store a maximum of len2 unique keys, where len2 is the length of S2, the dictionary-related operations remain efficient and contribute minimally to the overall time complexity. When we combine all these factors, we arrive at the overall time complexity of the algorithm, which is O, n1 asterisk len1 in the worst case. This is because the outer loop runs up to n1 times, and each iteration involves processing len1 elements. However, it's important to note that if a repeating cycle is detected early, the algorithm can skip unnecessary computations, leading to a significant reduction in the actual runtime, making it much faster than the worst case bound in practice. Now, turning to space complexity, the most significant contributor is the index2_map dictionary. This dictionary stores the values of count 1 and count 2 corresponding to each unique value of count 2% len2. Since there can only be at most len2 unique values for count 2% len2, the total space required for the dictionary is O, len2. Besides the dictionary, the algorithm uses a fixed number of integer variables such as count 1 and count 2, which require constant space of O1. Therefore, the space complexity is primarily determined by the dictionary, and the overall space requirement is proportional to len2. The overall space complexity of the algorithm is therefore O, len2, because the dictionary dominates the space usage, and its size is limited by the length of S2. To better understand the efficiency of this approach, let's compare it to a brute force method. In a naive implementation, we would explicitly construct the string S1 repeated n1 times and then count the number of times S2, repeated n2 times, appears as a subsequence. This brute force approach would have a time complexity of O, n1 asterisk len1 asterisk n2 asterisk len2, because it involves constructing and processing the repeated strings explicitly. Additionally, it would require O, n1 asterisk len1, space to store the concatenated string. In contrast, the optimized algorithm avoids constructing the repeated strings entirely and leverages cycle detection to skip redundant calculations. This optimization reduces the time complexity to O, n1 asterisk len1, in the worst case and to O, len1 plus len2, on average if cycles are detected early. The space complexity is reduced to O, len2, as it only needs to store the state information in the dictionary. To summarize the time complexity under different scenarios, the best case performance occurs when cycles are detected early. In this case, the algorithm avoids most of the iterations, resulting in a time complexity of O, len1 plus len2. On average, the algorithm's performance is closer to the best case due to frequent early cycle detection. However, in the worst case, where no cycles are detected, the algorithm processes all n1 iterations of the outer loop, leading to a time complexity of O, n1 asterisk len1. To mathematically justify this big O analysis, consider that each character in S1 is processed once per iteration of the outer loop, resulting in len1 operations per iteration. With the outer loop running up to n1 times, the total number of operations is n1 asterisk len1 in the worst case. Although cycle detection optimizes this process in practice, the worst case bound remains valid. Space complexity, on the other hand, is determined solely by the dictionary, which stores at most len2 entries, giving it a space complexity of O, len2. This efficient use of time and space makes the optimized approach significantly better than the brute force method, both theoretically and practically. One common mistake to watch out for is not handling edge cases properly. For instance, if either S1 or S2 is an empty string, the logic can break, leading to runtime errors or incorrect results. If S1 is empty, for example, no matter what values N1 or N2 take, the result will always be 0 because there's nothing to repeat. The fix here is straightforward: check for empty strings right at the start and return the appropriate result. Another issue is brute forcing the solution without optimization. Simply simulating the repetition of S1 and S2 for large values, like N1 or N2 being 10,000, can quickly lead to a time limit exceeded error. To address this, it's important to recognize patterns or cycles within the repetition process, which can drastically reduce unnecessary computations. Lastly, miscounting subsequences is a common pitfall when overlapping characters in S1 and S2 aren't carefully tracked. For example, with S1 equals ABAC and S2 equals AC, you might miss matches if you don't use a proper two-pointer approach or precise index tracking. A careful simulation of the matching process can help avoid this error. Another critical mistake is ignoring integer overflow, especially in languages like C++ or Java, where operations on large numbers can exceed the data type limits. If you multiply very large values of N1 and N2 directly, it could lead to incorrect results. The solution is to use modular arithmetic or larger data types, such as long, to safely handle these computations. Also, many solutions fail due to redundant calculations when patterns or cycles in the matching process aren't identified. If there's a repeating sequence in how S1 matches S2, continuing the same work repeatedly wastes time. Detecting these cycles early on allows you to skip redundant computations. By leveraging modular arithmetic and focusing only on the unique work, you can optimize the solution significantly and handle large inputs more efficiently. When tackling this problem in an interview setting, it's crucial to focus on identifying patterns or cycles. Interviewers are often looking for your ability to spot these insights, as they are key to reducing time complexity for large inputs. It's also important to clearly explain the trade-offs between a brute force approach and an optimized one. While brute force might be intuitive, you should articulate why it's inefficient and how recognizing patterns avoids redundant work. Additionally, make sure to emphasize your ability to handle edge cases, such as empty strings, no matches, or extremely large inputs, as this demonstrates thoroughness. Finally, be ready to analyze and explain the time complexity of both the naive and optimized solutions. For example, a well-optimized approach might run in O, N1 plus N2, or O, N1 asterisk len, S2, which is far more efficient than brute force. To prepare further, you can explore related problems, such as LeetCode 792, which focuses on subsequence matching, or LeetCode 115, which deals with counting distinct subsequences. These problems share concepts like pattern detection and subsequence handling, making them great practice. There are several approaches to solving this problem, each with its own trade-offs. The brute force simulation involves repeating S1 N1 times and simulating the matching process for S2 repeated N2 times. While this approach is simple to understand, its time complexity, O, N1 asterisk len, S1 asterisk len, S2, makes it impractical for large inputs, so it's better suited for gaining intuition rather than production use. A more efficient approach is optimized cycle detection, where you use a hash map to detect repeating patterns in the matching process. By identifying cycle lengths, you can calculate results efficiently, reducing the complexity to O, N1 plus N2. Although this method is faster, it's slightly more challenging to implement. Another option is the two-pointer technique, where you use two pointers to simulate the matching process between S1 and S2. This approach is simpler than cycle detection and runs in O, N1 asterisk len, S2, making it a good middle ground for moderately large inputs. However, it's less optimal than cycle detection for very large values of N1 and N2. Each method has its strengths, so understanding the trade-offs is key to choosing the right one for a given scenario. Great job! In this session, we explored how to solve problem number 466, count the repetitions, by breaking it down into manageable steps. We highlighted the importance of optimizing repetitive processes and detecting cycles to save computation time. Keep practicing similar problems, and feel free to like, subscribe, and stay tuned for more solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!